Alrighty, let's take a look at this problem from the top of page 3, where we're asked to calculate the empirical formula of caffeine. The first step is going to be to assume 100 grams. That's going to allow us to change all our percentages into grams. So for instance, instead of writing 49.48%, I can write 49.48 grams of carbon, 5.19 grams of hydrogen, 28.85 grams of nitrogen, and 16.48 grams of oxygen. So from our periodic table, we're going to grab the molar masses for each of these elements, which is going to allow us to convert all of these to moles. So looking at how the units cancel, I put the molar mass on the bottom, so grams is going to cancel grams, and then I'm just left with the moles of each element. So in your calculator, you're going to take the 49.48 and divide by 12.011. .19 divided by 1.0079. And 16.48 divided by 15.99. Once all the elements are converted to moles, we need to identify the smallest mole value. So it looks like for this particular problem, the smallest one is associated with the moles of oxygen. So we're going to divide all of the mole values by this smallest mole value. Doing this is going to allow us to establish the mole to mole ratio in the problem. So in your calculator, the 4.119 divided by the 1.03, that gives us 4. Here we're going to have 5, 2, and 1. And then to report the empirical value, we're going to do C4H5 and 2O1. And I'm just writing that this is the empirical formula. With mass percents, we only can get empirical formula. We need the molar mass to then figure out what the molecular formula is. But we're going to get to that type of problem in just a minute here. Alrighty, let's work together to calculate both the empirical and molecular formula of allicin. It's a component in garlic. So just like our previous problem about the caffeine, we have a bunch of mass percents. And we're going to assume 100 grams, which allows us to change the percents into grams. So it's 44.4 grams of carbon, 6.21 grams of hydrogen, 39.5 grams of sulfur, and 9.86 grams of oxygen. So we're gonna get rid of grams and convert each one of these elements into moles using the molar mass from the periodic table. Let's see, 1 mole of sulfur has 32.065 grams of sulfur. Alrighty, so looking at how the units are canceling, grams cancel with grams, and I'm just left with moles, and that holds true for each one of these. So I took 44.4 and divided by 12.011. I got 3.696. Now we're going to do 6.21 divided by the 1.0079. 6.16132 moles of hydrogen. For sulfur, I got 1.23187 moles of sulfur. And for oxygen, 0.6162885. Definitely the smallest one of the group, the oxygen down here. So I'm going to divide everybody by 0.6162885. And actually, that marker is not too. Try that one more time. 0.6162885. Anything divided by itself is going to give me 1. All right, so we have our multiple ratios, and we can definitely report out an empirical formula. So it's going to be C6H10S2O1. Now we want to work towards obtaining the molecular formula. The first step to do that is to calculate what I like to call an empirical mass. It's the same thing as like any other kind of mass, but it's for the empirical formula only. So empirical mass of this compound, well, we just figured out we have 6 carbons. So I'll do 12 times 6, and we have 10 hydrogens. Just estimating my values here, 10 times 1. 2 sulfurs. Sulfur comes in at about 32, so 32 times 2. And 1 oxygen. So if you throw that all on your calculator and get a mass, you get 162. If we compare that to this value, we see that they're one and the same. So we got 162 here and 162 here. Since the empirical mass equals the molar mass that they give us, we know that the empirical formula equals the molecular formula. Let me summarize that a little bit more formally. what you can do is you could take your molar mass and divide by your empirical mass. In this case, 162 grams divided by 162 grams. That's going to give you the ratio between the two formulas. The ratio is 1, so our molecular formula is C6H10S2O. If the ratio, if we did this and the ratio was 2, then we'd have to double all this. And we're going to see a problem like that later on. Or if it was 3, you'd have to triple all the coefficients. Alright, so let's tackle this problem about theobromine. It's a nitrogen-containing compound that's present in chocolate. So we're given the following masses. And just like when we're giving percents, and then we convert them to masses, our ultimate goal when we're looking for the empirical formula of any compound is to take the mass and turn it into moles. So let's take care of that. So step 1, mass to moles. So 1 mole of carbon has 12.011 grams. Grams of carbon cancel grams of carbon. I'm left with moles of carbon. And so here I'm looking at 0.0971193 moles of carbon. I'm going to repeat with the hydrogen. 1 mole of hydrogen from the periodic table, 1.0079 grams of hydrogen. Grams cancel grams, and I'm just left with moles of hydrogen. So 0.11102 moles of hydrogen. Next one, 1 mole of nitrogen. And I have 14.0007 grams of nitrogen. Grams cancel grams, and I'm just left with moles of nitrogen. So 0.055479 moles of nitrogen. And the last one here is my oxygen. So 1 mole of oxygen and 15.999 grams of oxygen. And I got 0.02775 moles of oxygen. So once all of the elements are converted to moles, you need to identify your smallest mole value, and in this case it's the oxygen. So everybody's going to get divided by that value. So 0.02775. Just going to write it underneath all of these. So for this first one, when we do our moles of carbon, we get 3.5. Hydrogen, I got 4. Nitrogen, 2. And since oxygen was our smallest of the group, it's going to be divided by itself. It's going to be equal to 1. So this is an interesting example because we have 3.5. when you have a number that's not super close to a whole number. So in previous examples, maybe like the answer was supposed to be 4, but we got 3.99. So we felt really comfortable rounding up to 4. I don't know what to do with 3.5. Do I round up? Do I round down? We can't guess like that. The appropriate approach here is to multiply everybody by a number that's gonna give us a whole number. So I'm thinking if I do 3.5 times 2, that'll give me 7. So that's a whole number, and our formulas have to have whole numbers. But since I did to the first one, I gotta do it to the second one. To our nitrogen, 2 times 2 is 4, and to our oxygen. So at the end of the day, I'm going to use all the numbers in blue when I'm writing my formula. I'm going to say it's C7, H8, N4, O2. And that will be my empirical formula. We weren't given the molar mass, so we don't know if it's the molecular formula as well. That will be the empirical formula of the theobromine compound that is in chocolate. Alrighty, so in this problem, we're given a molar mass, and we're asked to solve for both the empirical formula and the molecular formula of butyric acid. So I'm going to start with all my grams and convert them all to moles. So using our molar masses from the periodic table, looking at how everything cancels grams, I'm just left with moles. Alright, so 1.363 divided by the 12.011, and I got these values. Just like in all our previous examples, once we're at the point where we have everything in moles, you find the lowest mole value, which again is oxygen, and divide every mole value by that smallest mole value. Here I get 2, 4, and 1. So I'm going to use this information to write my empirical formula. You know, it's C2H4O1. The 1 is understood. Now I need to take this information and come up with a molecular formula. I'm going to erase this real quick. My first task is going to be calculating the empirical mass, what I like to call the empirical mass. The empirical mass is just like the molecular mass, except it's based off of the empirical formula. So I have 2 carbons, so 12.011 times 2, some grams in there, 4 hydrogens, and 1 oxygen. When I add that up, I get 44.0526 grams in total. Again, just to present it formally, we're going to take our molar mass and divide by that empirical mass. that's going to give us a ratio which tells us how much we need to scale up our empirical mass. So 88 divided by 44. And I get 2. So I'm going to take this empirical formula up here, C2H4O, and multiply it by 2. So I'll get C4H8, and there's a 1 here, right? So O2. And that's actually my molecular formula for the compound. Alrighty, for our next problem, we're looking at a compound that's present in garlic. I really love all of these problems because they represent an actual career that